Welcome back, everyone. So now we're finally going to start to put all of our knowledge about Lewis dot structures together to actually draw some Lewis dot structures of molecules on our own. So to do this, I think it's going to be instructive for you to have your periodic table in front of you along with this chart, because it's a good summary of the rules that you need to follow when doing Lewis dot structures for molecules. So we're going to use the example carbon dioxide, CO2, to illustrate the steps for drawing correct Lewis dot structures. So the first step that you need to do is to find the total number of valence electrons for your molecule. So to find the number of valence electrons for your molecule, you need to sum up the valence electrons for each atom in your molecule. So for example, carbon dioxide, carbon is in group 4, so it has 4 valence electrons. There are 2 oxygens, so we need to take the number of valence electrons for one oxygen, which is 6, multiplied by 2. And then when adding those together, that gets you the number of valence electrons that you will use when constructing the Lewis dot structure. So in this case, I have 16 valence electrons. I use no more, no less when doing the Lewis dot structure for carbon dioxide. If we were to be doing the Lewis dot structure for an ion, and we will be doing some of those in the next video, we need to take the loss or gain of that electron in that ion by either adding or subtracting. So essentially, if you have an anion, something that is negatively charged, you would add an electron for each anion charge that you have. If you have a species that's positively charged, or a cation, then you would subtract the appropriate number of electrons from your total valence. In this case, carbon dioxide, there's no charge on carbon dioxide. I don't see any charge as a superscript in the upper right-hand corner. So the total number of valence electrons that we will use is what we calculated here, which is 16. So that's the first step, find the total number of valence electrons. Second step is to write the skeletal structure of your molecule. Now, there are sort of 2 rules that we're going to follow when doing this. The first rule is that hydrogen, if you have a hydrogen in your molecule, hydrogen is always terminal, which means it's at the end of the bond. It's not a central atom. And then the next rule is that the atoms are usually in the order listed, with the central atom being first. So looking at carbon dioxide, how I've written it here, I have carbon as my first atom. And so that carbon is going to be my central atom. I've got carbon here as the central atom. And then I take my other 2 atoms, my other atoms that are attached to the carbon, and I scatter them around the central atom. In this case, I just put 1 oxygen here and 1 oxygen here. Now it doesn't matter if I was to put both oxygens over on the left-hand side or on the right-hand side, just as long as they surround the central atom, which in this case is carbon. Okay. So that's the second step. Write the skeletal structure, the first atom almost always being central, except if it's hydrogen. If it's hydrogen, then it needs to be terminal at the ends of the bond. And then the third step is to start distributing your valence electrons. And so we have 16 valence electrons that we calculated, so no more, no less. So we're going to distribute our electrons, and we need to do those in a very specific order, how we distribute them. The first step you do when distributing electrons is to make single bonds first. And specifically, when I say make single bonds first, that means a single bond, that means 2 electrons that are shared between the central atom and the outer atom. So in this case, since I've got two outer atoms, I'm going to go ahead and make single bonds by putting two electrons in between this oxygen and this carbon, and this carbon and this oxygen. I could have also just as easily used dashes, meaning something like this. I could have easily just used dashes in place of dots for the bonded electrons. Okay? But remembering that in single bonds, you use two electrons. Okay? So I've made single bonds from my central atom to my outer atoms. And when I do that, I need to be using my valence electrons. And so as of this step, I have used 4 of my 16 valence electrons. Okay? So I've made my single bonds. Now, with the rest of my electrons that are left, what I need to do is to complete the octets for all outer atoms. Okay? And when I say complete the octets, I mean make sure that each of your outer atoms, in this case the 2 oxygens, are surrounded by an octet, or 8 electrons. So doing that, I've used the 4 that are the in-between. And so doing that, I complete the octets on my outer oxygen atoms. And so at this stage, I have used a total of 2, 4, 6, 8, 10, 12, 14, 16. I have used a total of 16 electrons, and that's all that I have to use. I can't add or subtract any more electrons at this point. Okay? So I can't add any more. My oxygens are happy, meaning that they have an octet of electrons around them. But look at the carbon in this case right now. Right now, does carbon have an octet of electrons around it? It does not. It only has 4, the 2 that are in between this oxygen and this oxygen. So, and we need to make sure that you satisfy the octet rule when doing these Lewis dot structures, except for hydrogen and boron and helium. So how can we have carbon obtain an octet without adding any extra electrons? This is where you need to look on your outer atoms and see if you have any lone pairs of electrons that are available to make double or triple bonds. And yes, indeed, each oxygen actually has 3 lone pairs of electrons. So I can easily take a lone pair from each oxygen to share with the carbon, as is shown by these curved blue arrows. And so when doing that, the number of shared electrons between the oxygen and carbon increase. So my carbon now does indeed have an octet, but I didn't need to add or subtract any electrons. I still have a total of 16 valence electrons in my Lewis dot structure. And all of my atoms are happy, meaning they all have an octet of electrons. This oxygen on the left has 2, 4, 6, 8. My carbon has 2, 4, 6, 8. This oxygen on the right has 2, 4, 6, 8. So I've satisfied the octet for all my atoms. So this structure would be the appropriate Lewis dot structure for CO2. I could have also written it with those shared electrons in the form of double bonds, making sure though that I still show those lone pairs of electrons on the oxygen that are not shared. So those are the rules for determining or for drawing Lewis dot structures for molecules. In the next video, we're going to do 4 more examples, 2 of neutral molecules, 1 of an anion, and 1 of a cation to further solidify this point.